I
Morning, ma'am.
audible? Okay. So, first of all, I would like to know the names of the class representatives or any of the responsible students, so to whom I can contact for the scheduling of the lectures in case I need. So, first from the CSE third year, it's Jessie.
Yes, ma'am.
Uh, are you a class representative of CSE third year?
Yes, ma'am.
Okay, okay. And from a CSE final year, no one.
Hello. Yes, ma'am. I'm Subhasis from Final Year CSE.
Hello.
Hello.
Okay, from the CSE final year, yes, from the CSE final year, who will take
Yes,
the
ma'am.
responsibility?
Yes, ma'am.
What's your name?
Subhasis.
Subhashis. Okay, okay. Fine. And from the mechanical third year, mechanical third year, any of the student who can to whom I can contact. No one.
Ma'am, this is Basagar from Mechanical Third Year.
Okay. What is your enrollment number?
22, ma'am.
20, 22. Third, list. It's 32 or 20, 22?
ME
22.
19B22.
Okay, fine. And from a mechanical final year,
Good morning, ma'am. This is Karthik from Final Year Mechanical.
what is your enrollment number?
I'm M31.
31. Okay. ME 18 B1031.
Yes, ma'am.
Okay, okay. So I have to reschedule last day's lecture. So you just decide at what time I can take that lecture. Actually, the timing was clashing. So I scheduled it on today or at 3:40. But some of the students requested me that they have already some lectures at that time. So you tell me at what time I can take that yesterday's lecture, because you
Will
all
today,
we this yes,
will today be fine, ma'am? Today in the evening?
today evening. Okay, no issue.
Evening and afternoon, ma'am. Actually, we have
At
another
what
timing
time
also.
I scheduled? Yeah, I scheduled on 3:40, but from the mechanical final year, I think they already have one
Yes,
of the
ma'am.
class.
Actually,
Okay.
we said 3:40 p.m.
For 4:30. Okay, so is it okay if I take from 4:35?
Uh, can we have the class from 2?
Because two, I think from CSC they have they have issue.
Okay, ma'am.
2 o'clock, I think for CSC students having some another lecture.
Yes, ma'am. We have.
Yes. So what now you all decide what could be the suitable time. Okay. Jesse, can you
Yes, ma'am.
contact all these. Can you contact all these representative and let me know what could be the suitable time which for all the branches, because four branches are here enrolled for this subject.
Okay, ma'am. Sure.
Okay.
Okay, ma'am.
Okay. Okay. So one more thing is that for your attendance, uh, you have to write your type your enrollment number in chat box. Okay, for the attendance. Fine.
Ma'am, now?
Yes, you have 5 minutes.
Okay.
You right. Okay, so let's start. Okay, so we discussed about Quine McCluskey or tabulation method for the minimization of the Boolean expression. Okay, we discussed how to. Okay, so we discussed how to use this tabulation method, how to compare the min terms from the different groups to minimize the expression. Okay, Boolean expression. So we have formed two tables for that. After this, we can if we see here for the okay, the class timing is 11:10. So within 5 minutes, whoever is coming here, I will allow them, and after 5 minutes, I will not allow anyone, and I will not take their them as a they were present in the class. Okay, only I am allowing you for the 5 minutes only. So we have formed the two tables. Okay, so did you try to form did you try to compare the group from group 0 to 0 to group 3 by yourself? Did you try? Anyone have having any kind of doubt till now? Tell me about this first, because this is a very lengthy process. So if you have any kind of confusion, you just let me know. I will explain it before moving for the prime implicant table. No issue. Okay, so we have a possibility of minimization further here. If we see, if we observe this table, we have possibility of comparing further. Okay, so if we compare group 0 with 1, so we'll see that 0 1 will be compared with any of this min-term combination. One will be compared with any of this combination in the group 2, and here the elements of group 2 will be compared with any one of the elements of group 3. Okay, so this is the final table after comparing. So if we notice here, Okay, so if we notice here and if we try to compare further, we'll see that there is no possibility of further comparison. See, if we try to compare this group 0 with 1, what will happen here? 0 dash will be compared with here. 0189 will be compared with 13911. So we will see here dash is there, 00 is there, but 0 dash and dash 1. It's not possible. Okay, we'll compare 0189 19311. It will see that there's no possibility. Again, this is the same thing, so we don't need to repeat it. See, if from the group 1, if we compare 13911, we'll see, we notice that here it is not possible. So this is we can check this. So we can put star mark here. Okay, I said that if whatever is not checked, will add a star mark here. Okay, so whatever terms are having star mark, they will form the min terms, or they will form the prime implicants. Okay, so what will be the prime implicants here? Here dash indicates that variable is not the part of that that prime implicant. Okay, so that we will not take a dash. Here BC is there, and with their level 0 0 0. Okay, so the first prime implicant will be B dash C dash. So here these two are repeating. So 0189 So we'll take only one here. So for the next group, we see that B dash D is the makes the prime implicant. For the group 2, CD makes the prime implicant. Okay, so these three are the prime implicant. So after finding out the prime implicants, what we do in this tabulation method, we make the prime implicant table. Okay, we form the prime implicant table. What we do in the prime implicant table among those different prime, because this is very simplified expression, but so we got only 3 prime implicants, but when the number of variables increases, so the number of prime implicants will also increase. So among those different multiple prime implicants, we try to find out the essential prime implicant, which minimizes the expression into minimized form. Okay, so what we do, we just write the prime implicant terms. We in the second column, we write their min terms, which forms the prime implicants. Okay, in the first column, we write the prime implicant terms with in terms of the variables. In the second, in terms of their min terms value. Okay, next is the min terms. Okay, what is the meaning of this thing? Min terms. Here, whatever min terms, we are taking only those min terms for which the function is true. Okay, so we will take only those min terms for which function is true. So in this particular example, if we notice here, 0 1 3 7 8 9 11 and 15. Okay, so we will take 0 1 3 7 8 9 11 15. Okay, then we'll see in which prime implicant 0 is there, that which min terms belong to which prime implicant. Okay, 1 minute. Okay, so what happened here? We put a cross mark only at that position which where in that particular we'll see which min terms belong to which prime implicant. Okay, that's why we are writing here the decimal numbers too. So we see here zero min term belongs to which prime implicant here b dash c dash, so we will put a cross mark. Okay, next is 1 belongs to prime implicant, so we'll put the cross mark here. Again, next 3, it belongs to it is the part of b dash d and here cd. Okay, so this is the part of only cd. 8, it is part of c dash. 9 dash c dash and b dash d, so here the cross marks. 11, it is part of b dash d and c dash, and 15 is part of only. Okay, we have this is the prime implicant table. So how we find out the essential prime using this table? The essential prime we can find out using we have to observe this prime implicant those terms which is the part of only one prime implicant. Just try to find out only min terms which is part of only one prime implicant. Okay, one prime implicant. So this is the first step. So how many number of min terms are part of only one prime implicant? Tell me. It is visible that I have encircled with the red mark. So that is this is the whatever prime implicant is the part, whatever min term is the part of one prime implicant, we will highlight that those min terms. Okay, first we find out the min terms which min term which belong to which prime implicant. Okay, then we try to find out those min terms which are part of only one implicant. Okay, so here 0 8, okay, 0 8 is part of b dash c dash. Okay, and here 7 and 15, this is not part of any other prime implicant, so 7 and 15 is are also the part of only one implicant, cd. So from this simple theory, we conclude that b dash, c dash, and c are the first level of essential prime implicant. Okay, we will find out the essential prime implicant, and the essential prime implicant will be covered by those min terms which belongs to only one prime implicant. Okay, so here we see that 0 8 it belongs to b dash c dash, so this makes one essential prime implicant. Then 7 15 it makes these are the part of only one prime implicant, so this is also the essential prime implicant. Okay, so these two are the essential prime implicants. So next is we have b dash d remains. So now what about this? Is it the essential prime implicant or not? Okay, we will try to find out what about this. See. Okay, in the first level, what we do, we know that d c dash is the essential prime implicant. Okay, pi. CD is also the essential prime implicant. Okay, now we have to find out that whether b dash d will be the part of our minimized expression. So just delete these things, just delete. Okay, okay, then also delete these and this one. So in the second level, we try to find out. Okay, same rule will apply here. That we find out those min terms which is the part of only one prime implicant. So only one prime implicant is remaining here, which is b dash d. So by this rule, we can say that this will also make the prime but see here. These are the decimal. Okay, 1, 3, 9, 11. Okay, 1, 3, 9, 11. These are the min terms which as these min terms have already been covered by b dash, c dash, and c d. C 1 is part of b dash, c dash. 3 is part of this cd. 9 is part of b dash, c dash, and 11 is part of cd. So there is no need to take this prime implicant term in a minimized Boolean expression. Okay, so that's why only the minimized expression will contain only these prime implicant terms, not the third one. So b dash d, we can omit this thing. So we don't need this b dash d here. So the minimized expression will be b dash c dash plus cd. Clear? Clear or not? Any confusion? Any confusion? No? Okay. So we'll see. Next, we'll see. This is whatever example we consider here. In this particular example, we did not take any of the don't care term. Okay. So what about the don't care terms? Okay. Because in the K-map method, we used those main terms, those don't care term as a 0 or 1, depends on SOP or POS. Okay, so here we can also use the don't care terms to find out the essential prime implicant for the minimization. So here, suppose this is the example. A, B, C, D. The min term for this particular Boolean expression is 2, 3, 7, 9, 11, and 13, and it is having 3 min terms: 1, 10, 15. Okay, so just the way we have done everything without don't care condition, we will proceed like that only, grouping these don't care terms in terms of the number of ones. Okay, so what we have to take those min terms in the formation of the groups. So we form the group of number of ones. Okay, so we have we have 2, 3, 7, 9, 11, 13, 1, 10, 15. So for the group 1, because here 0 is not the part of this expression, so group there will be no group 0. So it starts from group 1, and the part of group 1 are 1 and 2. Here 1 is part of don't care term. Okay, it doesn't matter. We are using for the comparison purpose only. So here for the group 2 have 3, 9, 10, because it contains two number of ones. Here for in 3, 7, 11, 13, number of the number 1, 3, and last is the group 4, which is here only one element is there, which is also the part of don't care terms. We are using for the comparison purpose, for the forming of different sign. This sign indicates that all the min terms here has been checked off, has been compared. Okay, so if we see group 1, element of group 1, this is 1. If we compare this with 3, what happens here? 0, 0, 0, 0, 0, 1, 1, 1. So this is the only one variable change here. So this is this has been checked. This 1 is compared with 9, 0, 1, 0, 0, 0, 0, 1, 1. This is also has been checked. So we can put a dash here, dash 0, 0, 1. Next is the group element, group 1 element 1, and it will be compared with group 2 element 10. Okay, 0, 1, 0, 0, 0, 1, 1, 0. So this is also we can compare. So we cannot compare this. Okay, again next group 1 element 2 and group 2 element 3, 0, 0, 0, 0, 1, 1, 0, 1. So we can put a tick mark here. And 2, 9, 0, 1, 0, 0, 1, 0, 0, 1. We can just like this, just like we have done in the previous example, we will compare a group n with group n plus 1. So here 4 groups are here. So this is the second table is this one. This is the second table, comparison table, and after comparing this, we find out this one. Okay, so these are the min terms. These are the min terms. These are the prime implicant actually, A, B, C, D. So how many number of prime implicants are here? Tell me. 1, 2, 3, and 4. Okay. If we try to compare further, it is not possible. So that's why we are stopping here. And in the then we will, after this, what we will do? We will make the prime implicant table. So in this prime implicant table, first prime implicant is B dash D. Next is B dash C. Next one is CD, and next one is AD. Okay, so by in this example we have 4 prime implicant. So by the use of this prime implicant, we will find out the essential prime implicant with the use of, because here we have used the don't care condition too. So something will be different here. Okay, so here see, first we will write the number of the min terms. Then here B dash D. Okay. Okay, this will form the B dash D. This will B dash C. This will be B dash C. This is CD and AD. So next is CD and next one is AD. Okay. See, here there is a
Hello, ma'am.
difference. Yes.
Actually, we were
Yes. Any doubt? Yeah, tell me, any doubt? Okay, so here what happens? See, here because this Boolean expression contains the midterms and also the don't care condition. So in the don't care, here we write the first column contains the prime implicant, second column contains the midterms, and third column contains the number of midterms involved. Here the second column includes the combination of midterms, and third includes the different midterms. Okay, so here we will check which midterm belong to which prime implicant. Okay, so here three there's a difference. The difference between the without don't care condition and the with don't care condition. We will use don't care terms while for the in the comparison table. Okay, we for the grouping purpose, grouping of ones, we use the min terms, don't care terms. Okay, for the comparison purpose, we will use the don't care terms. But while preparing the prime implicant table, so in the third column we will not include the don't care term, because we are interested only the minimized expression for the min terms only, for which that expression will be true. We are not interested in don't care term, but we will use the don't care terms for the minimization, because if we don't include the don't care terms, the minimized expression will not be that smaller. The number of literals will be very higher. So to minimize the number of literals, we use the don't care term. So here in the third column we will exclude the don't care terms. Here only we will take those min terms for which the Boolean expression is, we will show the high value. Okay, here these are 2, 3, 7, 9, 11, 15. These are the min terms. Okay, so we'll see first. 2 belongs to which prime implicant. So it belongs to this second prime implicant. 3 belongs to 3 prime implicants, first, second, and third. 7 belongs to this prime implicant, and this 9 belongs to this first prime implicant and the last prime implicant, and 11 belongs to all the prime implicant, and 13 belongs to only one prime implicant. Okay, so the next step is to identify those min terms which belongs to only one prime implicant. We have to identify those min terms for which belongs to only one prime implicant. This is the first step to find out the essential level of to find out the first level of essential prime. The multiple levels are here. So here we see here this 2 belongs to only this one, and here this 7 belongs to only this one, and this 13 belongs to this one. So we will cross this this and this. Okay. So, and we will also delete these things. Okay. So the first level of essential prime implicants will be B dash C plus CD plus AD. B dash C, CD and AD, these are the essential prime implicant from this prime implicant table. Okay. So essential prime implicant are, we need to check whether the B dash D will become the part of this minimized expression or not. We need to check that too. So again, we'll check here. We'll see after deleting these things which min terms belong to only one prime implicant. Okay, we will check which min term belong to only one prime implicant. Only one prime implicant is remaining here. So here we see that 3 belongs to only one prime implicant. So if from the rule we can say that this will also be included in the minimized expression, but this is not the case because we have to check the number of min terms here. Here the min terms are 1, 3, 9, 11, but we also know 1 belongs to the don't care terms. So remaining min terms combination are 3, 9, 11. So we'll see. The 3, 9, 11 have already been checked, been considered in the first level of essential prime implicant. So we'll see here this 3, this 9 and 11. Okay, so these min terms are already have already been considered in the first level of essential prime implicant. So we can omit this term B dash D. So only the essential prime implicant will be B dash C, CD and AD. So the minimized expression will be B dash C plus CD plus AD. So this is the minimized expression. So this is for the four variable Boolean expression for 5, 6, 7, 8. So we can utilize this tabulation method to find out the implicant. Okay, clear? Any doubt? No one have any kind of doubt? Okay. So next topic is the implementation of Boolean expression using universal gates. Do you know what is the meaning of universal gates? Any idea what are the universal gates? Okay, what are the basic logic gates? What are the basic logic gates? Devendra? Okay, and or not. Okay, so any of the Boolean function, Boolean expression can be implemented. It's possible to implement the Boolean expression using these basic gates. Okay. So there are certain other types of gates, but the thing is that these are the very different gates. Okay, and or not. We say these are the basic logic gates, and these are the implementation is very completely different because their logic is different. So for the implementation purpose, the different combination of the their basic transistors or BJT will be involved for the implementation of this gates. So the combination, the basic formation of these three gates is different. Okay, and there is no possibility that these basic gates can be formed by each other. So there is no possibility that or we can implement OR gate with only AND gate or with NOT gate. not or AND gate we can there is no possibility that AND gate can be implemented with only OR gate. So if we use the basic logic gates, so we will have to utilize all the three basic logic gates. Okay. What is why we are using the why we need the universal gates? Actually, what happens if because this is the first step of the designing digital designing. After deciding the expression, after deciding the functionality, we have to implement with the help of the logic gates, and then those logic gates will be designed by some fabrication processes. Okay. So for the integrated circuit designing, for the fabrication process, it will be very easier if the circuitry is implemented with only one type of gate. So because there are a lot of steps are involved while we go for the fabrication, there are multiple levels of the steps are there. So the complexity is increases, and also the cost increases. So to reduce the complexity, to reduce the cost, we try to implement the functions with the help of only one type of gate. So those gates which gates which are able to implement the Boolean expression, the universal gates are the gates by the use of only that particular gate we will be able to implement any of the Boolean expression. So those type of gates are called as the universal gates. Why we are calling these gates as a universal gates? Because by the use of only one type of gate, whether it is because the basic with the help of basic logic gates, we cannot implement only one type of gate. We cannot implement the whole Boolean expression, but there are certain types of logic gates. By the use of only one that particular gate, we can implement the whole logic Boolean expression. So these gates are called as the universal gates. So there are two types of universal gates, NAND and NOR gates. These are the universal gates. Okay. So the NOR gate is basically is the in simple term is the not of OR. Okay, not of OR is the NOR gate. So the here it is indicated by A plus B dash or A plus B, because A plus B is the OR, and if we take the NOR of that OR, if we take the NOT of that OR, it will make NOR gate. So A plus B dash, it means if we take one OR gate which is followed by NOT gate. Okay, so it will make the NOR gate. This is the truth table of this NOR gate. Okay, it will be true when both the inputs are 1. NOR gate will be true when both the inputs are 0. Okay, and it will be 0 for other combination of the input. This is for the true 2 input NOR gate. Next is, we'll see we have in the basic Boolean expression theorems, we have seen there is a theorem called De Morgan's theorems. So there are two De Morgan's theorems. So it indicates that A plus B whole bar will be equal to A bar dot B bar. Okay, so according to this, if we try to make the try to implement this, okay, so it will be implement using the basic gates. It will be like this. So A bar dot B bar. So this is inverter, this is inverter, this is AND gate. So we can also write like this. If the bubble at the input side indicate that is the not thing. Okay, so we don't need to indicate by like this. So according to the De Morgan's theorem, a plus b whole bar will be equal to a bar b bar, and the symbol is like this. So from this theorem we can say that the NOR gate is equivalent to the bubble, because here the bubble in the input side indicates is the bubbled AND. Okay, so this is bubbled gate, so here it is the AND gate, so that's why we call this as a bubbled AND gate. So from this De Morgan's theorem we can say that the NOR gate is equivalent to bubbled AND gate. So for the conditions where there is a bubbled AND gate is there, because this principle we will use for the implementation of any kind of Boolean expression. We will utilize this De Morgan's theorem and this bubbled AND gate. So that's why we this, here from this De Morgan's theorem and from this comparison we can say that if we have some bubbled AND gate, we can replace this equivalently. We can use the NOR gate for the bubbled AND gate. So we will use this thing in the next lecture, how we can implement the universal gate and how the NOR gate implements the NOT basic logic operation like AND, OR, and NOT. Okay, any doubt till now? Anyone? Any doubt? No doubt? Okay, so in the next lecture, we will see how to use the universal gates. Those are the NOR gate and the NAND gate for the implementation of the Boolean expression. Okay.